Hello everyone and welcome to today's Crush the MCAT lesson on the periodic table and stoichiometry. First, let's talk about how we can read the table. The symbols we see here are the element symbols, and they describe what element is in each block. H is for hydrogen, Li is for lithium, and so on. The number above that element symbol is the atomic number here. The atomic number is the number of protons an element has, and this defines the element. For instance, if an element has 1 proton, it is always hydrogen. And if an element has 13 protons, it's always aluminum. Atomic number increases from left to right as we read the table. The second number we see is the atomic mass. The atomic mass describes how much the average atom weighs. The atomic mass is technically in atomic mass units, but we'll talk more about its significance in the next slide. Rows in the periodic table are called periods. For instance, this period from lithium to neon is a period, and columns in the periodic table are groups. One thing that's very important to understand about groups is that similar properties are grouped by column. All of the elements in this column have something in common, and we'll talk about that in a couple of slides. Let's talk next about the mole and atomic weight. The mole is defined by Avogadro's number, which is 6 times 10 to the 23rd. The mole is just a number, like how a dozen means 12, a mole is 6 times 10 to the 23rd. When we look at the atomic weight of an element, another thing it tells us is the molar mass of that element. For instance, if we look at helium over here, we can see that 1 mole of helium, meaning 6 times 10 to the 23rd molecules of helium, will weigh 4 grams. In this, we can say that helium weighs 4 grams per mole. Questions involving molar mass are likely going to require you to do a lot of unit conversions. I highly recommend you use the conversion table when solving these types of questions, and really any type of question that involves math. If you aren't familiar with the conversion table, I highly recommend watching our lesson on the conversion table. Let's take a look at our example question now. I'm going to draw out a conversion table first, and then we'll discuss the question. Alright, so here's the conversion table for this question. If we have 100 grams of O2, and we have a reaction that makes 8 moles of carbon for every mole of O2, the question is asking how many grams of carbon do we end up making? First, we start with the weight of O2, and then we need to convert the grams of O2 to the mole of O2. So how do we do this? We look over here to oxygen, and we see that oxygen weighs 16 grams per mole. But in our question, we have O2, not oxygen. Oxygen weighs 16 grams per mole, but O2, because it's double that, will weigh 32 grams per mole. Imagine, we have 6 times 10 to the 23rd molecules of O. If we have 6 times 10 to the 23rd molecules of O2, which weigh twice as much individually, then 1 mole of O2 will end up weighing twice as much as a mole of O. So we convert grams of O2 into moles of O2 this way. After that, we convert our moles of O2 into moles of carbon. So I'll cancel out these units here. And then finally, we get the grams of carbon. Simplifying our conversion table here, which we always do, we can turn 12 into 4 times 3, and we can combine the 8 and the 4 here to make 32. So then we can cancel out that 32 on top with the 32 on bottom. The only numbers we're left with on the top are 103, and on the bottom we only have 1. So we know that our final grams of carbon will be 300 grams of carbon. Again, the conversion table makes these unit conversions so easy, so I highly, highly recommend you use the conversion table. Okay, let's talk next about the groups of the periodic table. The first group you should be familiar with is the alkali metal group, which is everything in this column on the left. These metals like to have a +1 oxidative state. They like to give up their electron, and we'll talk about why in a second. So you'll typically see these alkali metals as Li plus or K plus. Next up, we have the alkaline earth metals. These will be beryllium and magnesium and everything below. These typically like to have a +2 oxidative state. So you will typically see these as beryllium 2+ or magnesium 2+, and so on. After that, everything under here is transition metals. And everything to the left of this line is going to be the nonmetals. There's nothing especially high yield that you need to know specifically about the transition metals or the nonmetals. Next up, we have the halogens here. This will be fluorine and everything below. These halogens typically like to have a -1 oxidative state, so you'll typically see these as chloride or bromide. And then finally, everything in the rightmost column on the periodic table is the noble gas group. What you should know about the noble gases is they have a full shell of valence electrons, and therefore they are very non-reactive. The AAMC also wants you to know about the representative elements and the oxygen group too. Okay, let's talk now about effective nuclear charge. This is a very important concept you need to understand in order to best understand periodic trends. So electrons orbit atomic nuclei in shells. We can see this on the diagrams below. Nuclei in the middle of the atoms are made of protons, which are positive particles, and neutrons, which you can consider the glue holding the protons together. Positive protons attract negative electrons. So if we look here, imagine there's a magnetic force which is attracting this electron and this proton together. If we go over to this next part of the diagram, we can see if we have more protons and more electrons, this magnetic force will be stronger. Because this force is stronger, these electrons will be pulled closer to the nucleus, and their orbit will be smaller because of that. Once an electron shell gets full, another electron shell is added. Full shells are stable, which makes noble gases the most stable elements. And remember, when something is stable, it is not very reactive. When we add a new shell, the electrons between that new shell and the nucleus are considered shielding electrons, which we can see for these electrons in the image on the right. Shielding electrons partially block electrons in outer shells from feeling the full attractive force of the protons. Conceptually, we can write this as effective nuclear charge is equal to the number of proton charge minus the number of shielding electrons. In other words, these two electrons feel a much stronger pull from the protons than this electron does here. So this electron on the outside has a lower effective nuclear charge compared to these two electrons, which have a higher effective nuclear charge. And again, those inner electrons have a higher effective nuclear charge because there's no shielding electrons between them and the protons inside the nucleus. So keep this concept of effective nuclear charge in mind, and it'll make periodic trends really easy to understand. To remind us what we talked about on the last slide, as we go left to right on the table, we increase our atomic number. This will increase the number of protons. And we can see that here in this diagram. When we go up to down on the periodic table, we're going to increase the number of shells. So a big difference between lithium and sodium is that sodium will have another electron shell. And then between potassium and sodium, potassium will have even another electron shell. So again, remember, as we go left to right on the periodic table, we increase the number of protons in the nucleus, which will increase the atomic nucleus's attractive force on the electrons. And as we go top down on the periodic table, we're going to increase the number of shells of those electrons, which get further and further away from the nucleus. With this in mind, let's talk about some trends. Remember, everyone wants the noble gas electron configuration. Noble gases have a very stable electron configuration. So that's the goal of all of these elements. Speaking about electron affinity, this is the energy released when an electron is added. Remember, when a reaction releases energy, those two things become more stable. So an element wants to release energy. If we look over here, fluorine has a high electron affinity because it really wants to add an electron to itself. Fluorine wants to become fluoride. And then same thing with chlorine here. Chlorine really wants to become chloride too. These two elements have a very high electron affinity because they really want electrons. If we look at something over here, like cesium, cesium does not want to gain another electron. Cesium minus would be a very difficult reaction to make. Therefore, cesium has a very low electron affinity. This same logic also applies to electronegativity, which has the same trend. Electronegativity is the affinity of a nucleus for electrons. So we can see why the fluorine nucleus has a very high affinity of electrons. Fluorine has 9 protons all clustered together, and it doesn't have very many electron shells. If we look over to cesium, cesium, because it's element number 55, will have so many shells. The electrons farthest from the nucleus, despite the nucleus having 55 protons, will be so far away that they won't feel much of an attractive force between the outer electrons and the inner nucleus. So the nucleus doesn't want to pick up another electron. That's why instead of seeing cesium minus, you'll usually see cesium plus. It would be easier for cesium to just get rid of one of its outer electrons and get that noble gas electron configuration. Atomic radii increase going down into the left. Again, that's because going down, we are increasing the number of shells. As we increase the shells, they get farther away from the nucleus. And atomic radius will increase going to the left because if we look at a certain row, even though boron and fluorine have the same electron shell, boron has much less protons. So we can look at this diagram up here to remember when we get less protons, despite having the same shell, looking between this one and this one, if we have the same shell but if we have less protons, those electrons will be farther away because they're feeling less of an effective nuclear force. Ionization energy is the energy it takes to strip an electron from an element, and generally this increases up and to the right. Remember, this is the energy that it takes, so a higher ionization energy means it will be more difficult to take an electron. Again, looking at fluorine here, it would be very difficult to make fluorine into fluorine plus. So the ionization energy of fluorine will be very high, because this reaction probably is not going to happen very easily. And again, if we look at cesium all the way down here, like we talked about before, that electron on the very outer shell of cesium, which is very far away from the nucleus, can easily be taken from cesium, and that will turn cesium's electron configuration into xenons, which it really wants to do. So the ionization energy for cesium will be very low, because it will be very easy to take an electron from cesium. One thing you should also know about ionization energies is first and second ionization energies. This is an important difference to remember between alkali metals and alkaline earth metals. If we draw out something like potassium going to potassium plus, that will have a low ionization energy because this reaction is very favorable. It won't take much energy to do it all. But if we go to K plus 2, that will be a very difficult reaction to happen. That reaction will take a lot of ionization energy because K plus already has the electron configuration of argon. It does not want to lose it. So this first ionization energy will be pretty low, and then this next second ionization energy will be very, very high. If we compare that to something like calcium, calcium going to calcium plus might have a low ionization energy, but calcium plus going to calcium 2 plus will definitely have a low ionization energy. Because again, calcium is gaining the noble gas electron configuration, which it wants to have. So remember, for periodic trends, you don't have to memorize anything, you can always work it out. If you think about effective nuclear charge, also remember, everyone wants the noble gas electron configuration, and that will help you out a lot too. Let's double check our understanding with these graphs. The first thing we have here is ionization energy. Remember, this is the energy it takes to strip an electron from an element. we can see here that the ionization energy for our noble gases is going to be extraordinarily high. That's because everyone wants to have the noble gas configuration, so once you have it, you don't want to lose it. Meanwhile, the ionization energy for lithium, sodium, and potassium is going to be very low because these very much want to lose their electron so they can become Na+ or K+, and so on, and get that noble gas electron configuration. For the atomic radii trend, we can see here, again, helium, neon, and argon, our noble gases, have very tight atomic radii. When you go from that noble gas electron configuration to having an entirely new electron orbital, in the case of our alkali metals, because you add an entirely new valence shell for that one electron, the atomic radius gets much bigger. And then again for electron affinity, which is the energy released when an electron is added, we can see that fluorine and chlorine release a lot of energy, which remember means it's a favorable reaction and it wants to happen when they get that electron. That's because these elements want to become fluoride and chloride. All these elements down here have no interest in becoming their negative forms. You never want to see helium minus or magnesium minus. This would take a lot of energy to create, and therefore the affinity these elements have for more electrons is very low. Okay, next up, let's talk about balancing equations and formulas. First, always be aware on the MCAT. You should balance any equation you should see. The MCAT might give you unbalanced equations and then ask you questions about that equation. I'm going to write out an equation now and we'll balance it together with the tip in mind that you should balance unique atoms first and then do the most common ones like oxygen and hydrogen last. Okay, here's our equation. Before we balance it, I want to take a look at all of the atoms we have in this equation and see which ones are unique and which ones stick out. Right off the bat, I can see we have calcium here, so I'm going to keep a special eye on that, and then we have a phosphate group here. Okay, let's take a look at the right side. Over here, we can see this molecule starts off with 3 calciums and 2 phosphate groups. I want to focus on one of these at a time. So first, I want to look at the calcium. I see we have 3 of them, and on the left, we have a molecule with just 1 calcium. I'm going to try now to put 3 here and see if that works. With this, I have 3 calcium, which checks out on the left and the right, and then I have 3 OH2s, which means I have 6 H's and 6 O's. Taking a look at the right side, these might be accounted for with the H2O, but we'll keep them in mind for now. So I'll write that out. We have 6 O's and 6 H's, which still need accounted for. Next up, we look at the phosphate, and we see we have 2 of those phosphates. So on the left, I'm going to write a number 2 here. With this 2 here, I see now that I have 2 H3s, or I have 6 more H's. I'll write that out here. So, on our right side, our calciums are accounted for, our phosphates are accounted for, and if we add up these oxygens and hydrogens, we're left with 12H and 6 O's, which we can say is the same as 6 H2O's. So now we have our balanced equation. Okay, next up, talking about percent mass. If you're asked to find percent mass, you need to divide the weight of atoms by the total weight of the molecule. Let me write out an example now. Okay, so let's say we have the molecule carbon monoxide here, and we're asked to find the percent mass of carbon and oxygen in this molecule. What we need to do is find the total weight of this molecule, which we can do by adding the weight of carbon, which is 12 grams per mole, we can see that here, and oxygen, which is 16 grams per mole, and we can see that here, and these both add up to 28 grams. Next up, we need to divide 12 by 28 to find carbon's contribution, and 16 by 28 to find oxygen's contribution. 12 over 28, if you divide by 4 on the top and bottom, can simplify to 3/7. And then 16 over 28 You could do the math again, or you know that these both add up to 1, so you know this simplifies to 4/7. If you're asked to find this answer in percent, don't overthink it. You know that 3.5 is half of 7, so 3/7 is going to be a little under half, or 40%, and 4/7 is going to be a little over half, or the remainder, so you know it's going to be 60% approximately. Now let's do an example where we're given percent mass. Let's say we have a molecule that we know is 36% carbon and is 64% oxygen. What we should do is we should use a 100-gram sample to convert these percents into grams. So all we need to do is just convert 36% into 36 grams of carbon and 64% oxygen into 64 grams of oxygen. Now we just use those same molecular weights we had before, and we can convert 36 grams of carbon if we divide by 12 grams per mole of carbon. We get 3 moles of carbon. Doing the same on the right and dividing by 16 grams per mole for oxygen, we get 4 moles of oxygen. So now we know in this molecule that the ratio of carbon to oxygen is C3:O4. However, this is only the empirical formula, which is the ratio of atoms in a compound. The true molecular formula of this compound can't be known just from this information, because it could be C3:O4 or it could be C6:O8. In the case of C6:O8, the percent carbon and the percent oxygen is exactly the same as it is when it's C3:O4. And I have some other examples of molecular versus empirical formulas on the right here. Lastly, I want to shout out this website here. If you want any more help balancing, identifying, or predicting chemical equations, I highly recommend you go to this website and spend a little time here. You can find the link here, and I'll also put it in the description too. And that concludes our lesson on the periodic table and stoichiometry.